Very good morning. Today we are going to see about the formulation of economic load dispatch problem. So if you see the definition of economic load dispatch, it goes like this. Okay, optimal allocation of generating units to the generating stations. Okay, with satisfying the demand and also with the and also we have to satisfy the minimum fuel cost. Okay, the fuel cost is to be the minimum. Okay, so we have to. So the main objective of economic load dispatch is to minimize the total fuel cost. We have to minimize the total fuel cost incurred in the all the generation. Okay, so what might be the objective function of economic load dispatch? To minimize the total fuel cost. So already we have formulated this. Okay, f of p, that is total fuel cost, ft of p is equal to summation I is equal to 1 to n fi of pa. Already we have formulated this. So this is the main objective function of your economic load dispatch. Okay, so as I said, every optimization problem has its own objective function and as well as the constraints. Okay, so here the objective function of economic load dispatch is to minimize the total fuel cost. Okay, so where I is equal to 1 to n. N is nothing but number of generating units that is participated in that particular dispatch. Okay, number of generating units. Say for example, one day dispatch you are taking only for thermal generating units. So it might be involved some 10 thermal generating units. So n is equal to 10. Okay, like that. So f1 of p1 plus f2 of p2 up to f10 of p10. That we need to add. Next, whereas f of I of PA, we already derived this. We have derived this. That is AI PI squared plus BI PI plus CI. That is rupees per hour. We already derived this. No need of much explanation. If you are having any doubts in regarding this formulation, you go through my previous videos. That is AI PI squared plus BI PI plus CI. Okay, so you can also use PGI squared or PGI, like that you can use. Here also FI of PGI, like that also you can use. Okay, nothing to worry about that. PGI also same, PI also same. So for simplification, we have used here PI. You can also use PGI square. Okay, so that also it is possible. Okay, so this is the main objective function. And also fuel cost characteristics also we have seen. Okay, so this is in this axis we are taking the fuel rate. Okay, fuel cost. Okay, fuel cost, that is in rupees per hour. So in this axis we are taking that is power generation, maximum power generation in megawatt, max power generation in megawatt. So as well as the fuel cost increases, automatically your power generation also increase like anything. Okay, in the linear gradual manner. Okay, as well as the fuel cost increases, power generation also increase in this linear manner. So this, minimum, there is some minimum power generation to that of maximum power generation. So okay, more the fuel cost, more the power generation. If you are spending less fuel, power generation also will be less. Like say for example, if you are running a two-wheeler, if you are spending more to the fuel, okay, for petrol, more to the like petrol, so you can run for more kilometer. Okay, 1,000 kilometer you can run if you fill the fuel like that. Okay, if you fill off tank like that, you can go up to 500 kilometer like that. Okay, so similar, in the similar way, more the fuel cost, that is coal cost you have spent, so more the power generation also, not only the coal. So whatever the resources if you use here, so based on that, power generation also will be increases. But for hydro generation, this fuel cost is not this much. Okay, so that is free only, but some maintenance cost is there. Okay, so we have to give the salaries to the employees, wages to the employees, like very minimum cost. It is of not very high cost. It is of very minimum cost. So in that thing, this fuel cost might be of very less, and the power generation also will be more because resource only free, and minimum cost, the characteristics will come some around like this. Okay, so based on the every resources, you can draw this fuel cost characteristics. So here this is mainly meant for the thermal generating units. Next, what are the constraints? As I said, there are two constraints. One is power balance constraints. Power balance constraints is nothing but, so whatever the power generation, that is like a PGI. Okay, PGI, that is equal to the demand, or PI. Okay, whatever the power generation for from I is equal to 1 to n generating units, that is equal to the demand. Okay, say for example, here it is 100 plus 500 plus 1000 plus 2500 plus 4000, like that. So demand also will be the same demand, because based on the demand or load only we are generating, no. So that is called your power balance constraint. Here transmission network loss are not considered. Transmission network losses are not considered. So the first constraint is power balance constraint. So in optimization point of view, this is the equality constraint. Okay, equality constraint, that is so equal to symbol is there now. Whatever the functional value, that is equals the resource value. Okay, this is in optimization point of view, that is equality constraints. In optimization point of view, it is a equality constraints. So here it is power balance constraints. So next constraints is that minimum and maximum operating limits or power generation capacity limits. Okay, minimum and maximum operating limits are power generation capacity limits. Okay, so here whatever the power generation, that should be within the minimum and maximum operating limits. Say for example, like 1000 megawatt is the power generation. So minimum power generation that is specified for that particular generator is, say for example, some 850 megawatt or 900 megawatt. So maximum power generation is some 1020 megawatt or 1030 megawatt. So you have to operate the particular power generator within this limit only. You should not exceed, and you should not go beyond this limit also, and you should not exceed also. Like this power generation capacity limits is there. Okay, next, coming to the problem formulation. Okay, by using lambda iteration method. So there are many methods, there are n number of methods to solve this economic load dispatch problem. So this is one such a method. Okay, there are n number of optimization techniques. If you take the algorithm, minimum 200 algorithms might be there. And if you take the problem formulation, minimum some problem formulation, using normal mathematical method, it is also having some 10-20 methods are there. And there are many methods. Okay, it is not only specified this method is very correct, or there are many methods are there. One such method is lambda iteration method. So in this lambda iteration method, we are going to solve this problem using Newton method, Newtonian's method. I think you have studied that Newton's method in your basics physics classes and basic mathematics also. Newton method is very accurate method of solving the problem. Okay, Newton method, you will get a very accurate result, but the time involved Okay, if you take like the time involved in the method is very more, but you'll get very accurate answer if you solve using your calculator. Then this method is good method, very good method to for solving the this problem. Okay, so let's go into the this lambda iteration method. Okay, so here we are neglecting the transmission losses. Okay, neglecting the transmission losses. So for this lambda iteration method, first you have we have formulated objective function and as well as the constraints. Okay, so objective functions is in your hand and constraints in your hand. Now we have to solve the problem. Okay, we will solve using the Lagrange's function method. So what is Lagrange's function method is in the sense Lagrange's function is defined as objective function plus some constant into constraints. Okay, I think you have studied this Lagrange's function method in your basic classes in your engineering undergraduate courses, like in your mathematics, in your mathematics 1, you might have studied this Lagrange's function method. Okay, or otherwise in mathematics 3 also sometimes you will be using, but mathematics 1, I think in the first or second unit you'll be having this Lagrange's function method. Okay, in Lagrange's function method, how to define this Lagrange's function in method in the sense Lagrange's function is defined as objective function. So here, say for example, this is the objective function plus some constant into constraints. Okay. So objective function, what is the objective function here? Minimize the total fuel cost, that is Fi of Pi. Okay, Fi of P is the objective function plus constant we are adding this as lambda. Okay, so you might have come across one question like why you are adding lambda like that. Okay, so this method itself lambda iteration method, so we are adding the lambda. Say for example, you can also name your own name, something like that, your name and iteration method. You can also use instead of lambda your name here, or otherwise any constant, your first letter of your name also here. But this is the lambda iteration method, so clearly we are using lambda. Or otherwise you might have come across question, why can't you use alpha, beta, gamma, like that you can use. But some formulation lambda iteration method, it is formulated, so we are using the lambda over here. Okay, so what is the constraints here? Here it is power balance constraints, that is PGI is equal to PD. Okay, PGI is equal to PD. This is the power balance constraint. Okay, so as a whole we have formulated the Lagrange's function. Excuse me. As a whole we have formulated the Lagrange's function like this. So generally if you see like any if you take the any load, okay, Pi so general formulation is Pi minus PD. Okay, so if you take any load, this PD will be very more. PD will be very more. Why? Because PD is nothing but demand, power demand. So whatever the power generation, say for example, the whole state total load is today is the 15,000 megawatt. The whole state load is 15,000 megawatt. Okay, but the power generation also around the 15,000 megawatt. But we can't predict the load correctly. It might be varying. Like anything. If you stand in load dispatch center, I will explain you the load dispatch center in one separate class. If you stand in the load dispatch center, you will get the online you will get the load. Okay, the load is varying like anything. So 15,000 megawatt is the total load of our state now. Okay, if you consider like this, the generation also around the 15,000 megawatt. Okay, due to the ever increasing in the load, we can't tell like this is the particular load. Why? Because every time we are purchasing new appliances. Say for example, Pongal time, New Year time, Christmas time is there, then Diwali we celebrated. So every new festivals, what we'll do, we'll go to the nearby shops, electronic shops, we'll purchase one new components, new equipments for our betterment. Okay, new washing machine, new refrigerators, then new induction cookers, induction stoves, then induction cooker is there, then microwave oven is there. Whatever we want, okay, they are giving some good offers now. We'll simply go and we'll purchase that new components. Like day by day, the appliances might be adding. Okay, it is not decreasing. Okay, due to our sophistication, we are increasing the new the like vessel washing machines also there nowadays. Okay, vessel washing machines also, but little bit costly. But even though we are purchasing, okay, so simply like that, if you keep the vessels, it will wash and it will come out. So like new appliances we are buying. So the demand is increasing like anything. We can't predict the demand is now it is 15,000 megawatt. It might be going up to like 15,000 50 megawatt, 15,020. Then it will suddenly decrease to 14,920, or suddenly to 14,500, and suddenly in minute by minute and second by second it might be vary. But in the load dispatch center, second by second means they will get confusion. So minute by minute or 5 minutes once, they will update the that data. Okay, so it might be going up to 15,002 megawatt, then 15,005 megawatt. Suddenly, it is decreasing to 14,999, 14,990, 14,800, then five. Like that, it might be decreasing and increasing, decreasing, increasing like that. Okay, so how they will increase the generation in a sense, if the demand is maximum for like 15 minutes or half an hour. Okay, so half an hour, it is demand is constantly maintaining as 15,000, say for example, instead of 15,000, 15,020 megawatt, or 15,050 megawatt, like that 15 minutes constantly it is maintaining na, they will start another 50 megawatt in some other generating. But even though they will not generate very correctly, just for an example, for understanding purpose I am telling, they will not generate very correctly to the demand. They will increase the generation by some 100 megawatt or 500 megawatt, because to induce the reactive power. Okay, that reactive power also very big concept that will see in the forthcoming classes. Okay, so this reactive power also plays a vital role. So for reactive power generation, they will increase 100 or 200 megawatt, or to the maximum of 500 megawatt. But for example, I am telling you, but the if you take like demand is varying like anything. Okay, demand is varying like anything. So generation, so practically demand is more. Practically demand is more than the generation. So what we are doing is we are taking the demand this side. Okay, so even though Pi is equal to Pd, so we can also write this equation like this also. Pd minus Pa also we can write. Why? Because why we are writing like this? Because practically speaking, demand might be increasing like anything. Okay, than the generation. Than the generation. If you go to internship to nearby load dispatch centers, then you come to know this concept. Okay, so in the free summer time, you can go for one internship to your load dispatch center, not your substation like that. Load dispatch center, you try to go for that. then you might be knowing this concept very clearly. Okay, so here, so we have rewritten this constraint as PD minus PI. PD minus PI. So generally demand might be more, so we are neglecting this term. Neglecting this term. So how to solve this Lagrange's function, in the sense we have to differentiate excuse me, we have to differentiate this Lagrange's function and equate it to 0. We have to differentiate this Lagrange's function and equate it to 0 with respect to Pi. With respect to Pi. So why we are going for this differentiation, in the sense we are going to find out the small change. We are going to find out the small change in the that generation that is happening. Okay, generation that is happening. So that's why we are going for this differentiation. Okay, so here it is, this term is neglected. So what we are doing is we are differentiating this Lagrange's function with respect to Pi, with respect to Pi. So while differentiating, this is the f of I into P divided by dpi. This is f of I, only f of I. This is a function of Pi. Okay, so all the terms what is f of I of Pi is in the sense ai Pi square plus bi Pi plus c, no. So this is the function of, so then that's why we have added this p here. Okay, this is the function. Okay, this is a function of P. Okay, power, function of power. So dfi into P divided by dpi plus lambda into, so if you differentiate this term will become 1. Okay, because here it is Pi, so here this term will become 1. So minus 1 is equal to 0. Okay, so what we are doing is we are equating it to 0, differentiating Lagrange's function with respect to Pi and equate it to 0. Okay, equate it to 0. So what we are doing here is, so here df of I into Pi divided by dpi minus lambda is equal to 0. Like simplification, we are doing the simplification process. So finally we have attained this df of phi into Pi divided by dpi is equal to lambda. Okay, into lambda for Pi minimum less than or equal to Pi less than or equal to Pi maximum. That is lambda is equal to, okay, lambda is equal to df of 1 divided by divided by dp1, then d equal to df2 of p divided by dp2 equal to up to df of n into p divided by dpn. Okay, so I is equal to 1 to n, no. Okay, so this is the condition, final condition that we have attained. That is df of p divided by dpi is equal to lambda for Pi minimum less than or equal to Pi less than or equal to Pi maximum. Okay, so so this is equal to condition. If df of I divided by dpi is less than or equal to lambda, then Pi is equal to Pi maximum. Okay, if df of I divided by dpi is greater than or equal to lambda, then Pi is equal to Pi minimum. So these are the three condition, optimality condition we have derived for this economic load dispatch using lambda iteration method. This is the economic load dispatch of n thermal generating units committed to serve the common load P load. Okay, economic load dispatch of n thermal generating units. Say for example, in the thermal generating units, you will have boilers. Okay, boilers that is being given to that from the boiler. So boiler here, what we have to do is we have to create we have to give the heat for enormous amount of heat to this boiler. Okay, if you take the temperature of the boiler, it is around 500 degrees Celsius, 600 degrees Celsius, like that will be generating in the boiler. Okay, enormous amount of heat. It is not a very normal heat, enormous in the house we are boiling. What is the maximum boiling point of the water is, in the sense it is 100 degrees Celsius. So 100 degrees Celsius, we are heating the water in our houses, 100 degrees Celsius. But if you take in the like 100 degrees Celsius, you can't keep your fingers, hands inside that water. Okay, it will be very, very hot. Okay, but if you take like a normal thermal generating unit system boiler, it is of that temperature of 500 degrees Celsius, 600 degrees Celsius, 700. It goes up to, depends on the generation, power generation. This boiler temperatures also increase like anything. So enormous amount of heat is being given. So what is the fuel? Fuel means the coal. Coal is nothing but the fuel. Okay, so fuel cost of first unit boiler. First boiler is F1. We are taking the fuel cost of first unit boiler. Say for example, in the boiler one, in the stage one, you are using good quality of the coal. Okay, we are taking the good quality of the lignite. Okay, in the that is the fuel cost of one, F1. Okay, fuel cost F1. So that is being given to the boiler B1, boiler 1. So here, enormous amount of heat is generated. From this, we are making the steam, superheated steam. Okay, so not normal steam. Okay, so we are taking steam inhalation. No, in that steam inhalation, in steam inhalation itself, we can't able to tolerate. If you just inhale that for sometimes, like a few seconds only, we can able to inhale that steam. If we are doing no steam inhalation, but you imagine about the superheated steam. Okay, like it is of um, superheated steam, in the sense for 100 degree itself, 100 degrees Celsius, we are boiling the water, we are inhaling that steam. Superheated steams means 500 5 to 6 times more. 5 to 6 times more means, if you take your hand inside that superheated steam, maybe your hand might be you may lose your hand also, because it is like the heating of that superheated steam like anything. Okay, if you keep a normal plastic or something also, it will melt. Okay, that much amount of heat, superheated steam. It is not a normal steam. Superheated steam is hitting the turbine. Okay, so that's why the turbine size. Okay, it is hitting the turbine size of 500 megawatt, 1000 megawatt. Okay, 500 megawatt. Imagine the 500 megawatt generator size. Maybe your room, your classroom size. Okay, classroom size or more than that also. Okay, so that much the turbine has to turn. Okay, that much pressure, with that much pressure the turbine has to turn. Okay, yeah, so if you want any doubts regarding this, how the turbine is getting turned, everything, you just go through my previous videos. Yeah, I have explained it clearly. Okay, so here it is out of topic. So superheated steam is generated and it is turning the turbine. Okay, it is turning the 1000 megawatt turbine or 500 megawatt turbine or more than that also. So that turbine is being coupled with your generator, with your alternator, and exciter also there. That also you will be finding the explanation in my previous classes. Okay, so here the generator is rotating and producing the power of P1. So first, from the first generator, the power is generated around P1. Okay, and we are giving to a common bus. Okay, common bus. Okay, and next, same story. Similarly, second generator, the fuel cost is F2. Okay, fuel cost is F2. Here we are using somewhat more some low quality of lignite, whereas This first unit cost is, say for example, 12 rupees. This second turbine cost, second boiler unit cost is some 10 rupees, like that. Some third is somewhat some 8 rupees, like that. Okay. For an example, I'm telling you. Okay, like that, some low quality coal we are using. Okay, so next, boiler 2, same heat, some heat is generated, then the superheated steam is being given to the turbine 2, and it is turbine is rotating, and as well as your generator is rotating, and it is producing the P2. Similarly, Fn up to Fn. Okay, Fn boil, because we are taking n generators. No, similarly, third generator, say for example, third generator, here it is. Okay, so third generator, third fuel cost, then boiler, third boiler, then the turbine is T3, that is being given to the generator G3. Okay, from the generator G3, we are producing the power of P3, and we are giving to the this bus. Okay, and up to FAN. Okay, nth generators also same concept. Nth generator Fn, boiler N, this turbine Tn, generator Gn, and power produced is in the sense Pn. That is being given to the common bus, and satisfying a load, some load or demand, some P load, say for example P load. So this story you need to write in write after this diagram. Okay, whatever I told, that you have to write. Okay, so this is the economic load dispatch of n thermal generating units committed to serve the load. So after this, after drawing this, you need first you need to define the economic load dispatch problem, that already I have defined that. Next, you need to draw this n thermal generating units committed to serve the load. This story you need to write. After this, you have to go for the objective function formulation. Objective function formulation we already seen before. What is the objective function of the economic load dispatch? Minimize the total fuel cost, that is Fi of Pi. Okay, minimize the total fuel cost, that is Fi of Pi. And what is the constraint? First constraint is power balance constraints. That is power generation that equals the demand. Okay, this constraint. That is summation I is equal to 1 to n, Pa is equal to Pd. That the demand, that is the power balance constraint. Next, what is the next constraint? Next constraint is that second constraint is the minimum and maximum operating limits, or minimum and maximum capacity limits, or everything is same. Okay, maximum operating limits is that is PGI minimum less than or equal to PGI less than or equal to PGI maximum. Okay, so these are the constraints that you need to explain about each constraints. Next, after that, we need to formulate the Lagrange's function. Lagrange's function also you need to define. Okay, already I have defined what is Lagrange's function. Lagrange's function is equal to objective function plus some constant into constraints. So objective function, what is the objective function? Minimize the total fuel cost. So what is the constant? Constant here is lambda. So what is the constraint? Constraints is this, that is power balance constraints, that is PD, Pi is equal to PD, but due to the demand is more. Okay, we are considering the demand is ever increasing like anything, so demand is more because we can't predict the demand. So by that time we'll on the television, by that time simply we'll off, by that time we'll simply on our like ACs. So after some half an hour simply will off. By the time some half an hour the load may increase, not because of your load it will not increase, but even everyone is thinking for the same. So climate is suddenly hot. Okay, so what everyone will think, some those who are having ACs, they will simply on for sometimes some half an hour or 1 hour, like that. So suddenly the load might be getting increased. Okay, so after 1 hour or after 2 hours, they'll simply off. Suddenly the load might be decreasing. Okay, so not only AC I'm telling. So sudden some ceiling fan or something, some with the immediate something load, like that. So okay, so here the demand is more, so neglecting, so the demand is more, we are neglecting this demand. So after framing out the Lagrange's function, we need to find out the what is the change in the change in the fuel cost. Okay, change minimum. Our fuel cost has to be minimum, so we need to find a small change in the fuel cost. So that's why we are differentiating this Lagrange's function with respect to that PI and equating it to 0. If I want to find out the maximum, maximum change in the some maximum profit or maximum change in the fuel cost, like that, we need to integrate. Instead of differentiate, we need to integrate, and we need to find out the answer. So by integration, so while integrating, what we'll integrate from 0 to 24 hours. What is the maximum change, like that. You already solved many problems in your mathematics 3, I think, suppose. Okay, some the metal as heated. I think you solved a similar kind of the problem. The metal is heated for one piece of metal of 1 meter square, of rectangular type metal is heated up to some 200 degrees Celsius, and same it is cooled up to some 100 degrees Celsius. What is the variation in that particular steel? Something like that. You solve the problem. So in that scenario, what you did is some integration. You did some integration for this many hours. How long it is heated? Some 1 to 3 hours, something it is heated. Like that you solved some problems in your mathematics. I remember something in when I solved this mathematics. I think similar kind of problem also you might have solved. Okay, so here same. So here we are differentiating. Sometimes you need to integrate if the condition is maximum. Okay, so here it is, we need to find out the small change in the fuel cost. So differentiating and equate it to 0. Okay, so while differentiating, df of I divided by dpa plus lambda into this pdi, we are neglecting, so 0. So here while differentiating, it will become 1. So after simplification, you will get like this, like df I divided by dpa is equal to lambda. Okay, for pi minimum less than or equal to pi less than or equal to pi maximum. Okay, so here if dfi divided by dpi is less than or equal to lambda for pi is equal to pi maximum, then if dfi divided by dpi is greater than, that is change in fuel cost with respect to the power is greater than or equal to lambda, then we have to go for this condition, that is pi is equal to pi maximum. So these are the 3 optimality conditions you need to derive. Okay, 3 optimality condition you need to derive for the economic load dispatch of n thermal generating units without considering the transmission network losses.